Welcome friends, Igor is here, and in this video we will talk about geometric interpretation of vectors. Let's get started. We can think of vectors algebraically, in which case vectors are simply ordered lists of numbers. For example, a column vector is an ordered list of numbers that is written in a vertical fashion. But there is another geometric perspective on vectors, in which case vectors are thought of as objects that have magnitude and direction. This point of view is often adopted in physics. Let's try to find connections between these two different views on vectors, and we will try to illustrate algebraic properties of operations on vectors geometrically. If we start with a column vector, which is an algebraic way to express a vector, we can then construct the corresponding geometric representation of this vector as follows. We can think of the geometric vector, which is an object with magnitude and direction, as an object that starts at the origin and it ends at the point with coordinates equal to the components of the column vector. The starting point of a geometric vector is called its tail, and the ending point of the geometric vector is called its head. And usually we draw the arrow at the head of the vector to indicate the direction in which the vector points. But geometric vectors are defined only by magnitude, which you can think of as the length of the vector, and the direction. They do not come with naturally attached beginning and the end point, and therefore we're free to move geometric vectors around. For example, this geometric vector is the same as this geometric vector, which is also the same as this vector, and it is also the same as this vector. All these geometric objects point in the same direction and they have the same length, therefore they define the same geometric vector. But now, if we start with the geometric vector, we can then reconstruct the algebraic representation of this geometric vector. One simple way to represent a geometric vector in algebraic form is to move this vector so that its tail is at the origin, and then the coordinates of the head of the vector can be used as an ordered list of numbers for the algebraic presentation of the vector. For example, in this picture, this geometric vector corresponds to an algebraic column vector with components 2 and 1. We have defined the operation of addition on the algebraic vectors. Let's see how this operation translates into the geometric form. The first vector has components 2 and 1, and this means we can start with the origin, then move 2 points to the right and then 1 point up. The second vector has components -1 and 2. This means we can start with the origin, then move 1 point to the left and then 2 points up. To add vectors visually, geometrically, what we do is we move the second vector so that its tail starts at the head of the first vector. Then the sum of these two vectors is a vector that starts at the tail of the first vector and ends at the head of the second vector. To understand why it works out this way, for example, think of vectors as movement. The first vector says along the x-axis we move 2 points to the right, and then the second vector says we move 1 point back to the left. So the total movement corresponds to moving 1 point to the right. In the y direction, the first vector says we need to move 1 point up, and the second vector says we need to move 2 points up. So the total movement comprises 3 points up. Therefore, the total result is we have to move 1 point to the right and 3 points up. This geometric vector corresponds to the algebraic vector 1, 3. Next, let's visually represent the operation of scalar multiplication of vectors. We have an algebraic vector, and we know how to scalar multiply this vector. For example, we can scale this vector by a scalar 1.5, and we get a new algebraic vector. How does it work geometrically? Notice that with the geometric interpretation, you see that scaling the vector does not change its direction. You only change the magnitude of the vector. The vector still points in the same direction. Well, actually, Not quite, because if you scale by a negative number, then you change the direction to the opposite. Finally, let's see what happens when we start constructing linear combinations of vectors. So we start with two fixed vectors, and what I'm going to do is I'm going to draw random linear combinations of these vectors. To construct each random linear combination, I will draw two random numbers from the interval -3, 3, and I will use these two random numbers as two scalars in the linear combination of the given two vectors. This is what happens when we construct first 5 random linear combinations. Then we extend this to 10 random linear combinations, then to 20 linear combinations, and then to 50 linear combinations. I hope you see that as you generate more and more random linear combinations, your coverage becomes more uniform, and in the end, you will be able to obtain all possible vectors in the plane. There's one caveat, of course. To obtain all possible vectors in the plane, you would have to allow all possible scalars, not just those drawn from the interval -3, 3. So, should we mostly use algebraic representation of vectors or the geometric representation of vectors? Well, geometric representation of vectors helps us visually, intuitionally see what is going on. However, our visualization skills are limited. No one can visualize a 4 or a 5 or a 6-dimensional space. Yet, when you work with vectors algebraically, then the number of components is usually not a problem. You can just as easily work with vectors that contain 4, 5, or 6 components as with vectors that contain only 2 components. In this respect, an algebraic approach is more powerful, it is more universal. Yet the geometric view of vectors is still useful because it gives us some intuition on what is going on. It allows us to visualize possibly abstract and difficult algebraic operations. If you found this video useful, and I hope you did, please give it a like to help others discover this content, and of course subscribe to this channel to see more of these videos. I hope to see you later, infinitely many times. Have a good day.